The pyramids of Giza are among the oldest and most studied monuments on Earth. Built more than 4,500 years ago during Egypt's fourth dynasty, they have drawn archaeologists, engineers, and curious minds for millennia. Yet, despite that long history of study, these structures still hold many secrets. For most of that history, learning anything new about the pyramids meant going inside them, chipping away at stone, or reading what ancient sources had to say. But in the last few decades, a quiet revolution has taken place. Scientists have turned to spectroscopic and radiation-based techniques, tools originally developed for physics labs, medical imaging, and materials science, and pointed them at these ancient monuments. Today, we can peer inside the pyramids without touching them, identify pigments on artifacts without scraping them, and map chemical changes in 4,500-year-old stone without a single pickaxe. In this episode, A Spectroscopy Around the Globe, I will walk you through the major spectroscopic and related analytical techniques that have been applied in studying the Giza pyramids. From infrared thermography to muon tomography, from X-ray fluorescence to Fourier transform infrared spectroscopy, each technique tells a different part of the story of the Great Pyramids. Hello, everyone. My name is Will Wetzel, Senior Editor of Spectroscopy Magazine, and I am excited that you are joining me on this journey to Egypt today. I'm really excited to talk travel and spectroscopy with you. So I could have started this new video series with any famous landmark. So why did I pick Egypt? I chose to cover the pyramids at Giza first because I have a special connection to this landmark and to the country that it resides in. I grew up fascinated with ancient Egyptian history and culture. From first or second grade, which is when I learned about ancient Egypt, first through a Magic Treehouse book and then through an actual history textbook, I knew that I wanted to one day visit the Great Pyramid, the Valley of the Kings, and some of the other sites Egypt had to offer. And when I was a freshman at Villanova University, I got my chance. In the summer of 2015, I had the opportunity to join a summer abroad program in Luxor, Egypt, where my group got to explore most of the major archaeological sites in Luxor. So today, I thought I would revisit Egypt, but this time focus on the science behind the history. The Giza pyramids hold many secrets, and spectroscopy is helping to uncover them. Let's begin with a technique that's perhaps the most visually intuitive: infrared thermography. In October of 2015, an international team from Egypt, France, Canada, and Japan launched a project called Scan Pyramids. Its goal was to non-invasively scan 4 of Egypt's Great Pyramids, including Khufu's and Khafra's at Giza, using a suite of modern imaging technologies. The first tool they deployed was the infrared camera. Here's the basic principle. All materials absorb and release heat differently. Solid limestone heats up at a certain rate and cools down at a certain rate. Empty air does not. So if there's a void, a hidden corridor, a sealed chamber, a cavity behind a pyramid wall, it will appear as a temperature anomaly when scanned by an IR camera. The Scan Pyramids team conducted their thermal surveys at 2 key moments: sunrise, as the morning sun began heating the limestone from the outside, and sunset, as the stones were cooling down. By tracking the rate of that heating and cooling across the surface, researchers could identify where the stones were behaving differently from what you'd expect. The results were striking. Across all the pyramids studied, multiple thermal anomalies were detected, but one stood out in particular. On the eastern side of the Great Pyramid of Khufu, at ground level, 3 adjacent stones were running roughly 6 degrees Celsius warmer than the surrounding limestone. Most block-to-block temperature differences were only between 0.1 to 0.5 degrees, so 6 degrees was particularly impressive. What could cause such an anomaly? Possible explanations included empty spaces behind the surface, internal air currents channeling heat differently, or the use of different construction materials. No single conclusion was drawn at the time, but the anomaly helped guide the next phase of investigation, pointing researchers toward areas of interest to examine with more penetrating techniques. IR thermography has one key limitation. It only tells you that something is different. It doesn't tell you what that something is. For that, you need tools that could go deeper. So while IR thermography can tell us block-to-block temperature differences, it cannot peer inside the pyramids for us. To do that, researchers turn to cosmic ray muon radiography, sometimes called muography. This is where the science really gets genuinely extraordinary. Here's the background. Muons are subatomic particles, which can be looked at as the heavier cousins of electrons. And these are created constantly when cosmic rays from outer space collide with atoms in Earth's upper atmosphere. They rain down on us continuously, day and night, passing through everything around us. Unlike X-rays, which are blocked by dense materials over short distances, muons can penetrate hundreds of meters of rock before being fully absorbed. The denser the material, the more muons are absorbed. The less dense, the more of them pass through. This means that if you place a muon detector inside or beside a massive stone structure, you can essentially X-ray it by looking at the pattern of muons that make it through. Areas with hidden voids will let through more muons. Areas with solid stone will let through fewer. Now, this technique was first applied to the pyramids as far back as 1970, when Nobel Prize-winning physicist Luis Alvarez and his team placed muon detectors inside Khafre's pyramid, looking for hidden chambers. They found none, but they established that the method can work. Fast forward to the Scan Pyramids project in 2016 and 2017. Using 3 different independent muon detection technologies, teams from Nagoya University, KEK in Japan, and the French CEA independently scanned Khufu's pyramid. In November of 2017, published in the journal Nature, the Scan Pyramids team announced the discovery of the Big Void, which is a large, previously unknown cavity directly above the Grand Gallery, with a cross-section estimated to be comparable in size to the Grand Gallery itself. This was described as the biggest discovery inside the Great Pyramid since the 19th century. So how confident were the researchers in their findings? Very. The void was detected by all 3 muon detection technologies independently, and all 3 analyses agreed on its existence and general location. That kind of redundant confirmation is the gold standard in physics. The story did not end there. In 2023, the Scans Pyramid team provided detailed data on another corridor-shaped structure, the North Face corridor, behind the so-called chevron stones on Khufu's north face. Muon radiography had earlier suggested its presence, and eventually, physical inspection confirmed it. A 9-meter corridor hidden for 4,500 years had been found. Muon tomography continues to advance to this day. As of 2025, the SciDep collaboration is constructing new muon telescopes to scan Khafre's pyramid, the second largest pyramid at Giza, from multiple viewpoints, both inside the burial chamber and outside the structure. Their goal is to map any unknown internal structures that Alvarez's 1970 survey may have missed with far less sensitive instrumentation. And there is an even more ambitious project underway. The Exploring Great Pyramid mission, which plans to deploy a muon telescope system with roughly 100 times the sensitivity of what was used in the Scans Pyramid work. It will be capable of producing, for the very first time, a true 3D tomographic image of the entire Great Pyramid, something similar to a medical CT scan. So far, we've talked about techniques for mapping the large-scale internal structure of the pyramids themselves. But spectroscopy also has much to say about the smaller scale world, the materials, pigments, and artifacts associated with the Giza site. X-ray fluorescent spectroscopy, or XRF, is one of the most widely used analytical tools in archaeology and heritage science. Here's how it works. When a material is bombarded with X-rays, the atoms in that material emit secondary X-rays at energies that are characteristic of each element. By reading that fingerprint of emitted radiation, scientists can determine which chemical elements are present in a sample and in what proportions, without destroying or even touching the object. In a landmark 2026 study, researchers examined a 26th dynasty wooden statuette excavated from the Tari Cemetery in the Giza Pyramids area. Using XRF alongside other techniques, they were able to identify every pigment used on the sculpture, quantify the composition of paint layers, and distinguish original ancient materials from modern degradation products introduced during millennia of burial. The XRF analysis identified the presence of Egyptian blue, one of the first synthetic pigments ever created. This is comprised of calcium, copper, and silicon. The researchers also found red ochre, which is an iron mineral hematite, orpiment, which is an arsenic sulfide used for yellow, carbon black, and metallic gold. Each element's signature told part of the story of how this object was made 2,600 years ago. The problem, though, is that XRF spectroscopy does have key limitations. For example, it tells you which elements are present, but not how they are bonded together, not the molecular structure. That's where Fourier transform infrared spectroscopy, or FTIR, comes into play. FTIR works by shining infrared light at a material. Different molecular bonds absorb infrared radiation at specific wavelengths. The resulting absorption spectrum is like a molecular fingerprint. It identifies compounds like calcium carbonate, gypsum, silica, and organic materials with great precision. FTIR was used alongside XRF in the Giza statuette study to confirm the identification of pigments and binding media, and to assess chemical degradation. These kinds of molecular level insights are impossible to obtain by looking at the object alone, and they help conservators understand what conditions an artifact has survived and what conditions it needs to survive in the future. There are two other spectroscopic techniques that deserve mention for their role in the study of Giza-related materials, and that is Raman spectroscopy and X-ray photoelectron spectroscopy. Let's start with Raman spectroscopy. Raman spectroscopy uses laser light to excite molecular vibrations in a sample, producing a spectrum of scattered light that is highly specific to individual compounds. It is non-destructive and can be used with portable instruments in the field. Raman spectroscopy has been applied extensively to ancient Egyptian pigments and artifacts. It has helped confirm the presence of Egyptian blue, orpiment, hematite, and carbon black through their characteristic spectral peaks. Raman is particularly powerful when used in combination with XRF and FTIR, since each technique is sensitive to different molecular properties. Together, they provide a fuller picture than any one method alone. Meanwhile, X-ray photoelectron spectroscopy, or XPS, adds yet another dimension. XPS measures the binding energies of electrons emitted from a surface when it's irradiated with X-rays. This tells scientists not just which elements are present, but which chemical state those elements are in, whether a copper atom is in a pure metallic state, an oxide, a carbonate, or a chloride, for example. Studies using XPS on ancient Egyptian cartonnage have confirmed the presence of rare pigments like cinnabar and orpiment, as well as identifying degradation products of Egyptian blue. These molecular level techniques, when applied to artifacts from the Giza area, allow researchers to reconstruct not just what materials ancient craftspeople used, but where those materials may have come from, how they were processed, and how they have changed over thousands of years of burial and exposure. For the highest precision analyses, researchers can deploy synchrotron-based X-ray diffraction, or XRD. A synchrotron is a type of particle accelerator that produces X-rays of extraordinary intensity and precision, far beyond what a laboratory X-ray source can achieve. When those X-rays are directed at a crystalline material, the pattern of diffraction they produce identifies the crystal structure with extreme precision. In the 2026 Giza statuette study mentioned earlier, synchrotron XRD was used to determine the exact mineral phases present in pigment layers, distinguishing, for instance, between different polymorphs of copper minerals that would be indistinguishable by other means. The technique also allowed researchers to calculate the crystallinity index of the ancient wood itself, which is a measure of how well the cellulose structure had been preserved over 2,600 years of burial. Synchrotron-based analysis only requires tiny samples. In this study, just 1 to 2 square millimeters, making it suitable for use on precious, irreplaceable artifacts. The combination of minimal sampling and maximum analytical power makes it one of the most valuable tools currently available to heritage scientists. The story of spectroscopic investigation at the pyramids of Giza is, at its heart, a story about what happens when we apply the tools of modern physics and chemistry to the oldest monuments in the world. From infrared thermography, which reads heat signatures on the pyramid surface and flags anomalies suggesting hidden spaces, to muon tomography, to XRF, FTIR, Raman, and synchrotron XRD, each technique answers questions that no other method can. Together, they have revealed a hidden corridor above the Grand Gallery, a previously unknown passage on the north face of Khufu's pyramid, thermal anomalies at ground level whose origin is still debated, and precise chemical portraits of how ancient Egyptians manufactured their pigments and how those pigments have aged over thousands of years. And this work is far from over. New muon telescope arrays with 100 times the sensitivity of existing instruments are being designed. The SIDEP project is scanning Khufu's pyramid with fresh eyes. More artifacts from the Giza area continue to be analyzed with ever more powerful spectroscopic tools. The pyramids of Giza have kept their secrets for 4.5 millennia. But with the tools of modern spectroscopy, we are beginning to read them. Thank you all for sticking with me on this journey to Egypt today. Before we wrap up, I wanted to call attention to the miniature Egypt flag behind me. For this episode and most subsequent episodes, you will see that this country flag cam will be perched atop books about the country that is covered in this month's episode. I'll list all the books and their titles in the description. Not all countries will have books featured in the country flag cam, because either the books I read on them were terrible, or because I simply don't have any books on this country in my home library. And with that, we'll end our exploration of Egypt and the Giza Pyramids. Thank you for joining me on this journey today. If you enjoyed this trip, be sure to give us a thumbs up and subscribe below. Interested in traveling to Egypt? The latest up-to-date information can be found on the U.S. Department of State website. Thank you again for joining me on this journey, and I'll see you in the next episode. Until then, safe travels.